It's my pleasure to introduce today's colloquium speaker. Dr. Katherine Deibel received her PhD from Yale University in 2008. She was a visiting research associate at Argonne National Lab through the Joint Institute for Nuclear Astrophysics, and she joined the faculty of Louisiana State University Physics and Astronomy Department in 2011. Her research interests lie in experimental nuclear astrophysics, and she is going to tell us a little bit more about that. Thank you very much. Please welcome Dr. Deibel.
Clapping before the talk. Let's not overpromise here, okay? So hi, I'm Katherine. Nice to meet everybody. Thank you for the introduction and thank you for the invitation to come to Rowan. I've had a really fun morning meeting a lot of people and talking about a lot of different stuff. And now I'll tell you a little bit about my research and more generally my field of nuclear astrophysics and how we connect nuclear physics with how stars burn and explode and make the stuff that makes up us. So I like to start from the beginning. And at the beginning, as far as we know, there was the Big Bang about 13.7 million years ago. And shortly thereafter, a fraction of a second or so, all the protons and neutrons came into existence from the sort of quark-gluon plasma that existed at the time. And then 3-ish minutes after that, the first nuclei formed. So the universe had expanded and cooled enough such that the first protons and neutrons were able to come together to form the first few elements without being blown apart. The flip side of this is that the universe had expanded and cooled enough that there wasn't enough energy to bring together more than a few protons because, of course, like charges repel. And so the more protons you try to bring in, the more repulsion those guys feel. And at this point in the universe, you had just the sweet spot of enough energy to bring 2, maybe 3 protons together, but no more than that. And so where you're stuck here is with hydrogen, helium, and a small amount of lithium and beryllium until hundreds of millions years later when the first stars coalesce and begin to burn. And now we have the avenue to make all of the other elements that we see in the periodic table. I should say also, if you have a question, please feel free to raise your hand and I'm happy to answer. I don't know if anybody's been to Argonne before where I did my postdoc, but they interrupt all the time, so I'm ready. So this is a chart of the nuclides. For those of you who aren't familiar with it, I will walk you through it. I like get a line up there. Am I saying okay, maybe? Is this going to mess things up? I can't really read what it says. Okay, cool. Slightly better. Can I click on that too? Sweet. Okay. So this is a chart of nuclides, and it's basically like a periodic table on steroids. So a periodic table shows all the elements, right, up to whatever we're at these days, like 118, is it? 119, I forget. And this guy shows all the elements, but also all of the isotopes of those elements. So the elements are defined by the number of protons in the nucleus, and then isotopes just have different numbers of neutrons with those same number of protons. So the way to read this guy is we have the, here we go. We have the Z or the Y-axis, the number of protons, and the X-axis, the number of neutrons. So basically every row is an element, and then the little boxes along the row are the isotopes of said elements. Running along kind of the spine here, these black boxes are the stable elements, so live forever, never decay, and then anything that has a color to it is unstable or radioactive and will eventually decay towards that, what we call the valley of stability. So the other thing to notice is there's these little like highlighted numbers of protons and neutrons. We call those magic numbers. So I don't know what decade those were named, but you can imagine. And so the idea is basically similar to atomic structure, right? You have electrons around an atom that fill like lower energy orbitals and so on and so forth. And there are like gaps in energy, and the noble gases are very stable because they have a completely filled orbital and that sort of thing. Same principle with nucleons. Nucleons is just the term I use as an umbrella for protons and neutrons. And so you get to these points where you have filled an energy level, and then there's a big gap in energy before the next level. And so there's a very stable configurations. And so that's what those lines represent, is where we have extremely stable configurations of our nuclei. So anyway, back to the matter at hand. After the Big Bang, you have just a little itty bitty guy tipped down here with the hydrogen, helium, and some lithium. And then the idea is, okay, well, we want to figure out how all this other stuff got made. And this happens through a wide variety of burning processes in stellar burning and various stellar explosions and that sort of thing. And figuring all of that out, where these things happen, what processes are responsible, how much of what is made where, all of that kind of stuff is basically the field of nuclear astrophysics. And in the 50s, the late 50s, as this field was sort of coming into its own, this review paper by Burbage, Fowler, and Hoyle was written to sort of lay out the general framework for all of this. And since then, we've basically been trying to fill in the picture and figure out how, when, and where all of these things are created. And someday I will figure out how to insert Shakespeare quotes into my own publications, but so far, no luck. So to figure this out, it's a very multidisciplinary approach, which is part of why I think it's an interesting field to be in. So of course, to understand the galaxy and the universe, we look up and we take observations, and that provides a lot of the motivation for trying to understand how stars explode and what gets made. We can actually observe isotopic signatures by using gamma ray satellites to look at specific energy gamma rays that get emitted from specific isotopes. We can use things like pre-solar grains, which are basically just little teeny bits of stardust that get encapsulated into meteorites, fall to Earth, and we crack those suckers open and see like how much of one isotope is there compared to another, and can categorize where these grains come from, the different stellar sites that those grains were produced in. And that all gives us a glimpse into what actually might be happening up there. But to really understand what's happening up there, we need to understand the processes that drive the synthesis of these various isotopes and elements. And what drives them is, of course, nuclear reactions and nuclear physics. And so what my field, or my area of this field is in, is specifically trying to measure and study reaction rates, which is needed as the underpinning to understand how all of these different stars are burning and exploding and what gets made. And that's done through a variety of models, like these very computationally intensive stellar models that have all kinds of like crazy thermodynamics, plasma physics, all kinds of nutty stuff that I don't know anything about. But underpinning that, what needs to be fed into these really intensive models is an accurate nuclear reaction network, because that's what's driving the whole shebang, so to speak, and dictating how much energy is produced and what temperatures you get to and what actually gets made in these environments. And so all of these things basically kind of work together. And when we have our conferences, we get to talk to some of the people that do the harder stuff of modeling and observing and that kind of thing, and talk about what the needs are in the community that's based on all these different things. So starting at like a really sort of basic level about how we can look at nuclear physics to inform what's happening in stellar processes, I want to just start real basic with two of the kind of most, I don't want to say simple, but the more fundamental things from both an observational standpoint and from a nuclear physics standpoint. So right here, on the left-hand side, I'm showing, like the one of the most readily pieces of observational data that we have, which is the abundance of different elements in our solar system. Okay, so unsurprisingly, it's a log scale, right? So mostly hydrogen and helium, because our solar system is mostly the sun, and that's what's in it. And then you see, a bunch of different abundances for all the other elements, basically up to 100. And we can compare this with one of the most basic sort of fundamental things that comes from nuclear physics, which is the binding energy per nucleon of the different isotopes that we see in the chart of nuclides. So basically, like I said, protons repel, obviously. And so something's got to be holding those guys together so that we all exist and don't evaporate into a bunch of protons and neutrons, which would be bad. And so what that is one of the four fundamental forces, which is the strong force, or sometimes called the nuclear force. There's a very short range. So the protons and neutrons don't see each other basically and get attracted unless they're right next to each other, which is again good for us. Otherwise, we'd be a giant ball of protons and neutrons together, and that would be bad too. And so you basically have this energy holding the protons and neutrons together in the nucleus, and that gives them more mass, because its energy is mass, E equals mc squared. And so you can basically look at the amount of energy, this binding energy per number of proton and neutrons, to tell you something kind of fundamental about how the protons and neutrons are together in the nucleus. And what you can see comparing these two plots is that there's a peak at the same place in both, and by place I mean at the same isotope in both, at iron. So the maximum binding energy per nucleon in a nucleus happens at iron 56. And lo and behold, if I look at my isotopic abundances in the solar system, I see a big old peak at iron. And the reason is because if you're on this side of the binding curve, it's energetically favorable to fuse things together to get heavier. You get energy out when you fuse these lighter elements together. And once you get to that hump and you get over it, it becomes energetically disfavorable to do that. It's more favorable to break things apart in fission. And so what this means is that in stable burning, and up to the point where you have a supernova, you're basically producing heavier and heavier stuff until you get to iron. And then at this peak is basically, sorry, I swear it's here. We get supernova elements in the iron peak. And actually, we see this directly through the light curves of supernovae, which are driven by the decay of nickel and cobalt, which are in this sort of same iron peak. They're descendants, if you will, of the iron that gets made. And that is what you exactly see with these two isotopes. You have this sort of double peaked or sloped rather curve, okay? And then if you're before that region here, like I said, it's energetically favorable to fuse things together. And so this is sort of what is responsible for fusion in stellar cores. You basically just build up to heavier and heavier stuff by fusing protons or helium or whatever onto what you got. And you end up with this sort of like onion-like structure in a star until you get to this iron core and everything collapses and boom goes the dynamite. And so I should also say that the reason this peak exists from a nuclear physics standpoint is because this is the point effectively where the nuclear force starts to lose to the Coulomb force, because the nuclear force, like I said, only exists or only has a very short range. So if I'm a proton happily in my nucleus, I see attraction from the people right next to me. But the protons and neutrons that are a couple rows back, I don't even know they're there from the nuclear physics perspective. But if you're a proton, I know you're there. I can feel your repulsion. Sounds mean, but I can feel myself being pushed away from you because of us having like charge. And so every time you add a proton, it only gains binding from the nuclear force of its nearest neighbor, but it feels the push from all the protons in the nucleus. And so the iron element is that place where you sort of tip the balances from like, okay, now the Coulomb force is starting to win out and it's no longer energetically favorable to add protons to the nucleus. So that's sort of where that comes from. I meant to say that earlier. And then once you get past this iron peak, it's a big question of, well, how do you ever make anything past here if it's not energetically favorable to make those heavier elements with more protons? And the answer is, well, there's two constituents to every nucleus, and one of them does not have charge. It's a neutron. And so if you can just add neutrons, then you sort of overcome this problem of the repulsion due to the Coulomb barrier. And so all of the isotopes basically after this iron peak are produced via neutron capture. So absorbing neutrons, which makes really radioactive stuff, but then that can decay to stability and give you these higher mass isotopes. And so that's what you see like all through here. And in fact, when you look more specifically at the observations that people do of very neutron-rich environments after they've undergone this neutron-rich capture, what you see is a pattern like this. And what you see is that the abundances peaks actually line up with these closed shells that we were talking about before, because that's where the nuclei are happiest to be, in those closed shells. So the nucleus sort of stops there and then decays back to stability. And we'll talk more about this later if there's time. So that's all well and good. We can make some really basic connections between, some nuclear physics properties and some basic stellar observations of our solar system, but we like to be maybe a little bit more creative and intricate and understand the details a little bit better. And so I'll go back to this chart of the nuclei to be a little more specific, maybe too specific. There's a lot going on here. But this is, again, the chart of nuclei. So the black boxes, again, are the stable guys. Various shades of green and yellow are radioactive guys. And superimposed on this are a bunch of colored lines that basically represent different processes that can happen in different stellar environments, okay? And so you don't have to concern yourself with all of them, but we figure out what those processes are by doing our observations, our modeling, and inputting nuclear physics. And one thing you'll notice is that several of these lines lie pretty far off stability. And this is, of course, because who doesn't like a challenge, the area that I'm most interested in, because probably unsurprising, there's not a lot known because unstable nuclei go away. So they're harder to study in the laboratory. And so a lot of our work at LSU and work of my colleagues has to do with figuring out how the processes that are responsible for element synthesis far from stability happen, because those are some of the really big open questions in our field that still need to be answered. And of course, they're very challenging to study because they're radioactive nuclei. So I'll be focusing on, well, in theory too, we'll see how time goes, processes, the two that are farthest from stability. The RP process, RP just stands for rapid proton capture. So the name sounds what it is, you capture protons rapidly. And our process stands for, you guessed it, rapid neutron capture, because we're a creative bunch. And that is thought to now happen in neutron-star mergers as opposed to other things, thanks to our friends at LIGO. And so we'll start with the first guy. So the fact that you're on the proton-rich side of nuclides here, so everything to this side of the valley of stability has more protons than stable stuff, which means that you're probably having these processes occur in somewhere where there's a lot of hydrogen, a lot of protons that are available to you. And one such environment is type 1 X-ray bursts, which you can see a little artist rendition of here. So they are explosions that occur in binary star systems. Turns out more than half of the star systems in the universe are actually not single stars like our sun, but binary stars. I did not know that, and I thought that was interesting. So now I'm telling you. And you have a neutron star at the center. And even though it looks like way smaller, and it is way smaller than the main sequence star that accompanies it, it's super dense, okay? It's like, I usually look up an analogy to the place I'm going when I give talks like this, but I forgot, and so I'll just use my LSU analogy. But it's basically like you took the Earth and you smooshed it up and put it in LSU's football stadium. Like, that's how dense a neutron star is. And so it sucks all the matter, or not all the matter, but the surface matter of this main sequence star onto its surface. And as that happens, the pressure, the temperature, the density, all these things build up until you have thermonuclear runaway. And this is a little movie, which is kind of lame, but still fun, that shows this process. You have a disk, it's falling onto the surface. There's stable nuclear burning at this point, but then eventually you have a thermonuclear runaway and you have a stellar explosion that makes lots of isotopes up to proton number 50-ish or so, so the 10 region. And you'll notice that after, things go off and then become more pixelated, I guess, the thing still exists, right? I think a lot of times people think of stellar explosions and they think of supernova where everything gets obliterated and you're done. But these types of things go off over and over and over again. It's a cyclical process. And that's really interesting for a couple of reasons. One is that there is a huge wealth of observational data because most of these things go off on the time scale of every few hours to every few days. So you can just like point your telescope and just kind of get a bunch of observations. And so there's a huge amount of observational data out there for these types of systems. And because the neutron star is so dense, most of the stuff that actually gets made gets sucked back onto the surface of the neutron star and is then the seeds for the next explosion that goes off. And so the main observable for these things are light curves. So you're just looking at photons that get emitted during the explosion. It looks like this. There's a huge steep rise and then an exponential decay. And this is sort of a typical X-ray burst. Each one of these two lines is about 10 or so observations averaged together for statistics. But the two different lines are from a set of observations that were several years apart. And that's because the system is evolving as the ashes build up, and so it changes over time. And understanding how that changes and understanding the shape of the decay can lead to all kinds of interesting information about not just neutron stars, but like nuclear physics in general. And the equation of state is a big thing. If you don't know what that is, I can tell you about it later. It's not really my jam, but like it's an interesting thing. In my job talk, someone asked me what the Nobel Prize was in my research, which is a terrible question to ask a job candidate, but that's the answer I came up with. So it's that kind of important question. Anyway, so the duration of the burst is just 10 to 100 seconds or so. And like I said, there's a wealth of observational data. And so these are driven, of course, by these nuclear reactions. And to understand what nuclear reactions are possible, you need to understand your constituents that you're starting with, okay? So like I said, the companion star is typically a mainish sequence star, which is full of hydrogen and some helium. And then the neutron star, people think of neutron stars as neutrons, which is true, but not in the upper layers. They're actually made that have a layered structure that are made of different isotopes. This is a more like prettier version. So you have a core that is neutron stars, or maybe even something more exotic, but then you have the heavy element ashes and then some layers from the accretion and the stable burning that happens in between the actual explosions. So they're not just neutrons. And so from this information, we can come up with some ideas of what reactions might happen in this type of environment that drives the stellar explosion and creates the heavier elements. So if we look at this from like a super simple perspective, let's say we have a nucleus on the crust of the neutron star that as the thing starts to go off and explode, that nucleus has a Z number of protons and N number of neutrons, and then it's going to react with something, right, during this explosion. And what do we have to react with? We have hydrogen and some helium, basically, is what's being accreted on the surface. So what can you do with this? So the first thing that's obvious that you can do is you can just fuse with a proton or a hydrogen nucleus, and that increases your proton number by 1. So Z plus 1 keeps the neutron number the same. And usually when this happens, the nucleus, this new element that gets created, is created in an excited state. So just like, again, just like atoms can have electrons promoted to a higher energy level and be in an excited state, so can a nucleus. It can have more energy and be in an excited state. Nature doesn't like to be excited. It likes to be lazy. And so it will emit a photon to get back to the ground state. That's one thing that can happen. You can have the exact opposite thing because there's lots of photons running around. So you can actually absorb one of those photons, be promoted to an excited state, and then emit a proton to decay. If you are already unstable or radioactive, you're going to want to, again, decay to stability. And that typically happens by emitting a beta plus particle, which is a positron, the electron counterpart, which changes effectively a proton into a neutron and brings you back down to that valley of stability. Because remember, we're on the proton-rich side of the chart of nuclides that I showed you earlier. And then we also have helium, like I said, that's part of the stuff that's being accreted onto the surface of the neutron star. So helium-4 is also, oops, where are you? Oh no. Helium-4, also known as an alpha particle, there he is, could also be fused with the nucleus, leading to an isotope that has 2 more protons and 2 more neutrons than what you started with, again, in an excited state, so emitting an alpha particle. And finally, you can do the same thing, but that excited state can decay by emitting a proton. And this is a so-called alpha P reaction. And so, I mean, all of these individual possibilities look pretty simple. I mean, you're basically just taking 2 particles and fusing them together. But of course, this is happening on a wide variety of nuclei that are in your crust and happening all really fast, creating more nuclei that can then fuse with more protons or alpha particles and so on and so forth. And things get real quick. So things get really complicated pretty quickly. And you can see there's a crazy amount of arrows here. And to hammer home the point even more, this is a simulation of an X-ray burst put together by the good folks at GINA. And again, we have a chart of nuclides. The bolded boxes are stable, and then everything that's not bolded is a radioactive isotope. And the burst starts to go off, and you can see lots of boxes lighting up as those elements are produced as the explosion starts. Red means there's a lot, blue means there's a little. And that's the scale. You can see time and temperature down here. I should say these things peak at about 2 billion Kelvin, 2 gigakelvin. You hit the peak, and then you keep going higher and higher up to the tin tellurium range, and then you eventually start to decay back to stability. And so it's like find a cute, colorful movie. But the thing to take away from this is there's a lot of stuff happening, right? There are literally hundreds of isotopes, hundreds of those boxes that are lighting up. And so to understand the whole, explosion well, and to understand the energy created, the light curve that might be made, so you can compare with observations, to understand the elements that get produced, you need to understand those reactions, okay? And there's literally thousands of reactions and decays that are happening during this 10 to 100 second period. So like, what's a nuclear astrophysicist to do? Like, I only have so many grant dollars and I'm going to retire. This is my goal. And so I don't want to like be doing this forever. So one way to figure that out is through what we call so-called sensitivity studies, where you basically have a model, like a computer model that, you know, models the X-ray burst going off, and going into that model is a list of reactions, these 3,000 reactions and decays that have rates attached to them, most of which I should say are theoretical, because like you saw in that movie, all those boxes that were lighting up were pretty far from stable nuclei, so they've mostly not been measured. So all of these rates maybe are, I mean, uncertainties of factors of 100. So, and so you basically put in all of these rates to the model, and then you do it again and again and again and over again, each time changing just a single rate by that theoretical uncertainty of about a factor of 100 or so, depending on how much you trust your theory. I'm not a theorist, so 100. And so you can see what happens. And so each one of these little light, so the black like bolded curve is the baseline with like the purely standard theoretical rates run in this model. And then every colored line is the output of the simulation with just one of these reactions changed. And you can see there can, in some cases, be a really dramatic effect on the shape, the length, the peak height, all these things of the light curve that gets produced just based on one single reaction. And of the 3,000 over reactions, there's actually not too many that have this big of an impact, which is good, because it basically takes that list of like thousands and makes it like 40, which is like a much more digestible number. And so this is the sort of like top 20 or 19, I guess, reactions from this study specifically that they found seem to influence things. And there are two that I'm going to focus on, the oxygen 15 alpha gamma, and more specific or more closely the neon 18 alpha P reaction. And those guys are important and have such a big influence because they are actually the two reactions that link that stable burning that's happening before the explosion goes off to the thermonuclear runaway that is the actual explosion. Without those reactions, those two parts of the nuclear chart don't line up. So there's stable burning happening down here in the carbon, neon, or nitrogen, oxygen region. And then this is where the explosion happens. And this region in here links the two. And so as you can imagine, how fast those reaction rates proceed can have a huge impact on the nucleosynthesis that happens in the new environments, because that's what's feeding material into the explosion, into the thermonuclear runaway. So their rates can dramatically affect how that X-ray burst goes off and what happens. So we've concentrated a lot of our efforts on those reactions because they seem to be quite impactful. And before I go into some of the measurements that help us to hopefully determine what those rates are more accurately, we should first talk about what a reaction rate is. And so what is a reaction rate? I mean, the name kind of says it, right? It's the rate at which a nuclear reaction happens, but more like specifically, it comes from two key components. One is the fact that you are having reactions happen in a stellar plasma, okay? And so it's not like every proton in our sun has the same energy. We say the sun is at a temperature, right? But not every proton in the sun has the same energy, or we wouldn't exist, quite frankly, because the sun would fizzle out and die, and that would be bad again for us. But rather there's a distribution, and that distribution is typically given by the Maxwell-Boltzmann distribution, which some of you may have already seen in your classes and such, and that is shown sort of over here. And then, fortunately for us, quantum physics is a thing, because without it, again, the sun would fizzle out and die, and we wouldn't be here, because the energies, even at the very highest energies that exist in the Maxwell-Boltzmann distribution, you still can't overcome a Coulomb barrier to bring two protons in our sun together. It's like not classically possible. And so quantum mechanics exists, which means that there's a probability that you can, what we call, tunnel through that little barrier and make it to your friendly neighborhood proton and fuse together. And that is a very small probability, but it is not zero. And so that is, thank you, quantum mechanics is why we exist. And it drops like a rock. It exponentially declines the lower you go in energy. But happily for us, there's a little sort of intersection between the very high energy tail of the Maxwell-Boltzmann distribution and the very low energy tail of the probability for tunneling. And that is where reactions happen in stars. And we call this the gamma peak, and we're all very happy for it. And this is the only equation I show, I promise. Well, this is the one that's about to come up right below it. But when you basically take these two things, the mathematical quantity for the probability of tunneling through the Coulomb barrier and the mathematical expression for the Maxwell-Boltzmann distribution, and fold them together, you come up with this equation, which is, I know, looking meaningless right now, but I'll walk you through it. It depends on temperature. Okay, this mu is the reduced mass, so it's just the masses of the two things that are reacting. The temperature of the environment, and then there's an exponential dependence again on the inverse of the temperature and on the energy of the excited state in the nucleus itself, or rather the amount of energy above a specific threshold. So there's exponentially dependent on the energy of the state that gets produced in your final nucleus. Like we talked about in that really simplified diagram, when I absorb a proton, the final nucleus is in an excited state. So it's basically the energy above the required energy to absorb the proton is that energy. And then this omega gamma character, which is basically just a bunch of nuclear structure information. So nuclear levels have spins associated with them. For those of you who haven't taken quantum mechanics, don't worry about it. It's fundamental quantity. You'll be confused when you get there. We all are. But it's a thing. So it depends on the spins, and it depends on how wide the energy is. Like, again, quantum mechanics is a thing, and the Heisenberg uncertainty principle exists. So you can't determine with exact precision what energy this is. There's actually an uncertainty to it that's physical. And that's what these guys represent for the different ways you can create a state. And so if you want to measure a reaction in a star, you can basically go about it two ways. One is both the easiest and the hardest, which is a direct measurement where you basically try to reproduce what happened in the star in the laboratory. You say, okay, I care about the fusion of these two things. I'm going to accelerate one and slam it into the other and see how many times I get out the product that I think should be made. And now I will know the reaction rate. Practically speaking, this is extremely difficult, especially if they're involving radioactive ions, because those beams are really difficult to make and they don't have a lot of intensity. And even though 2 billion degrees Kelvin is really hot, it's not actually that much energy on a nuclear scale, like compared to, like, say, the binding energy of a nucleus. It's actually like 1,000 times less than the binding energy or more. And so this guy dropping like a rock up here is also hampering your efforts. So these can be done from time to time, but are extremely difficult. But the other thing you can do is measure stuff indirectly, where you basically produce the nucleus that's produced in the star, in the states that might be produced in a star, but in a totally different way that's a lot more tenable to do in a laboratory setting. So you pick a different reaction that deals with stable nuclei and has a high cross section or probability of happening that you can actually measure, you know, in a week at the laboratory instead of a year at the laboratory, which you will never get time to do. And so this is what we do, like both methods. When we can, we study things directly, but a lot of times we study the nuclear structure of the nuclei that are produced in different stellar environments to then go back to this equation and calculate the reaction rate so we can give it to our friends who model these things and better understand what is happening in the star. How do you guys feel? Feel okay? Okay. Okay. So like I said, I'm going to talk sort of dive into a specific example. I'm going to talk about the neon 18 alpha P reaction, which is one of these reactions that links the stable burning on the surface of the neutron star before the explosion goes off to the actual explosion, the X-ray burst itself. And so this is what it looks like from like so pretend like energy is on the y-axis here. So this is like the mass energy of the ground state of neon 18. You add an alpha particle or a helium-4 nucleus, you create excited states in what we call the compound nucleus, which is magnesium 24, and then those emit a proton to get to your final nucleus, sodium 21. Note that all of these things are unstable. Okay, so everything we're dealing with here is radioactive isotope, except for the alphas and the protons. And so how do you study this? If you want to do a direct study, this presents challenges because this is actually not even right next to the valley of stability. It's a few nuclei off. And so it's really difficult to produce in the laboratory. And helium is a gas, which is annoying, which makes targets harder to make. Their gas is less dense than a solid. And so it is also difficult that way. So it's a challenging experiment, but we did it. I'll talk about it later. But you can also do, again, the indirect thing where you measure these properties of these states in a different way and then plug them into your equation. And that can be done in a variety of ways. One is just through like you throw a different beam at a target, they and emit a different product, and the thing that's left over is the neon or the magnesium, 22 of interest, and you can measure what energy it's at and so on and so forth. There we go. And then you could also go backwards in time, so to speak, where you take the sodium-21 that is the final product of the reaction that actually happens in the star and add a proton to it and then emit the alpha. And that's a lot easier because hydrogen can be found in lots of different compounds with carbon, for example, so you can make a solid target. And this guy, the sodium-21, is actually closer to stability. You can see it has a longer half-life, so it's easier to make in the laboratory. The downside is that if these decays happen not to the ground state, you will miss this contribution to the real reaction rate because the beam itself is just created in the ground state. And so you're only getting part of the picture. And this led to actually a lot of confusion with the results that had been heretofore produced for this reaction. So this is a lot, I know. You can just ignore the top plot completely, I don't care. But the bottom plot is the important thing. So people try to measure this. It's super important, and it's been known for decades how important this reaction is. So people have tried like 6 ways to Sunday to measure this thing. And this is kind of a summary of all of those results. So what are we looking at here? The green dashed curve is just a theoretical calculation, which was why it looks so uninteresting. The black points here are that time inverse thing where you add the proton to the sodium-21 and do things in the backwards direction. The blue guy is sort of a compilation of a bunch of indirect studies of those different reactions to produce the magnesium states. And you can see that things disagree by like a factor of 24, which is not great. You're like not doing that much better than theoretical uncertainty at this point. And so it's been a big question for a long time, how to reconcile this and actually get accurate nuclear information to have an accurate reaction rate. And so we actually tried to measure this guy directly, which we did at Florida State University. They have an accelerator lab there, and we did it with the Array for Nuclear Astrophysics Studies. Oh, that's wrong. We changed the acronym. Whoops. Nuclear structure, astrophysics and structure with nuclei is what it is now. But anyway, let's call it Anison. And Anison is unique because it's what we call an active target. So in all nuclear physics experiments, you take a beam, you accelerate it of some isotope, you smash it into a target, and you see what comes out, right? And so to see what comes out, you have to detect those particles. And this is a situation, an active target is where what you use as the target is also the medium in which you detect the products from your reaction, okay? So basically, it's a volume of gas, specifically helium-4 gas, aka gas of alpha particles. And we have a radioactive ion beam of neon-18 that gets produced at Florida State. And it comes into this chamber. And as it enters the gas, it starts to lose energy. And it loses energy all along the way. And basically, what it lets you do is you basically are probing the reaction of interest at a bunch of different energies at once. So in typical experiments, you have a thin target that's like usually solid, and beam hits it, and you're basically just getting the beam energy. And then if you want to measure a different energy point, you lower the beam energy, you do it again, so on and so forth. It takes forever. And if you have a radioactive ion beam that is 1,000,000 times less than your stable ion beam, ain't gonna happen. You're gonna get like one measurement and your referees will give you a hard time. And so this kind of allows you to get the most bang for your buck from these very not intense radioactive isotopes. And then what we do is we take this like beam trajectory and we basically surround it with detectors. So there's 2 sort of sets of detectors. These 2 lines here represent a proportional counter. So basically there's a bunch of wires, some of which have a voltage applied to them. And as the protons that get made when this reaction happens, as the beam traverses this gas, fly out, they ionize the gas that's in this detector that was also the target. And those electrons get attracted to these wires and make a signal. And these wires have like a resistive property, so you can measure the time at both ends, and the time difference tells you where along the wire the proton went past. And then surrounding that are these barrels of silicon detectors. They're like very thin wafers of silicon solid state detectors that the proton then hits. And they are also position sensitive and tell you how much energy got deposited. And my math classes tell me 2 points make a line. And so I can retrace and figure out exactly where the reaction happened. And as a result, I can reproduce the sort of excitation energy spectrum of the actual reaction and figure out what's happening. So this is kind of a nice picture of that. So these little gold guys are the wires of the proportional counters, and the shiny things are the silicon detectors that I was talking about. So basically it's a barrel, but the top half of the barrel has been removed, so you can kind of see the guts of the detector. And so we've done a variety of experiments, more than is listed here. These are the most interesting for nuclear astrophysics. And one of them you can see is the neon 18 alpha P reaction that we did at FSU. These are some of the data. So this is showing the energy loss detected by the proportional counter, those wires, as a function of the energy deposited in the silicon detectors. And energy loss is dependent on how many protons you have on your nucleus. So you get different groupings depending on what species you are. So these are the alphas that get scattered, and this intense guy here are the protons of interest from the actual reaction. And you gate around those, and then you can actually see how many times this reaction happened as a function of the beam energy as it was losing energy throughout this entire target. And that's what this is showing. So this is the data. The blue stuff is the actual data from the experiment. And then we should use the same colors. But these green points are that time inverse reaction that I showed a couple of plots ago that were black data points in that plot. And then the purple is that compilation of all the other indirect measurements. And what you can see is that one thing that this experiment was able to do that previous studies weren't able to do is to basically see which neon or sodium-21 was produced in the ground state versus an excited state. It was the green arrows in that little figure I showed with the arrows earlier. You could produce different proton decays to different states in the final nucleus. And what they saw is that if you just looked at the ground state, it kind of agreed with these inverse measurements, and that a lot of the discrepancy was coming because the contributions from those proton decays to the excited states were really large. And so that kind of explained why some of these measurements just did not agree within a factor of 24 from each other, because they weren't measuring this component, or they were, and they weren't both doing the same thing. So that's why. So this sort of settled that issue. The annoying thing is that because of the beam intensity and the beam energies we were able to produce at Florida State, the only place we got pretty good measurements with like relatively small error bars were for an energy region that matched about 2 gigakelvin in the stellar environment, which, like I said, is the peak temperature that these X-ray bursts happen at. But remember, this reaction is responsible for the start of the burst. So actually, it proceeds when the temperature is quite a bit lower, and more like in this region where you're just under 1 gigakelvin. And here, like really big error bars or no data at all. And so we're like, well, this is all well and good, and we've cleared up some discrepancies, but we really don't still know the answer of what the reaction rate is in the energy region that we're interested in. So we proposed an experiment at Triumph up in Vancouver, and we did some redesign stuff. We replaced the proportional counter, those wires, with another set of silicon detectors for a variety of reasons that I can talk about later if anyone's interested in it. And most importantly, at Triumph in Vancouver, they can make a beam that's about 100 times more intense, and they can make it at lower energies than they could at FSU. So we'll be able to probe that region. And this is what we expect for our results in the black. And if you recall, the FSU measurements sort of ended around 2000 keV. And so we'll be able to stretch down like much farther into the region of interest with this experiment, which we ran in 2022 or tried to, and technical difficulties, they could not make the beam for us. So we just ate a lot of sushi instead. And we are going to try to reschedule it for the summer. In addition, you can also, again, do these indirect measurements. And I'm probably going to skip my entire second part of my talk, but that's okay. which is sort of, again, a different methodology towards trying to get this nuclear information where you produce the same nuclei that are produced in the star, but in a different way. And this is the approach that we've taken to one of those other breakout reactions from the stable burning into the explosion, which is the oxygen 15 alpha gamma reaction. So this is the other big sort of player in this, this thing. And the oxygen 15 beams that are out there, they cannot do it. There's just nothing, nowhere in the world can make a beam that will make this reaction measurable in a reasonable amount of time, at least for any grad student or funding agency. And so the idea is to, well, let's study then the states that get produced in neon-19, but in a different way. So we can calculate the reaction rate with more accuracy. And so we did that at FSU just a year or so ago. Again, at FSU, this is a big old 36-ton spectrograph. It's actually the spectrograph I did my thesis on at Yale. And then when the lab shut down, I called my old advisor and I was like, hey, what you do in that spectrograph? May I have it? And after lots of lawyers, they said yes. And so we moved it to Florida State and installed it and have been using it for science for the last 4 years or so, which has been really exciting to see sort of like a second go with it. And so we populated these states in neon-19 with a different reaction. So we used a solid target of fluorine-19, which is stable. It's in the target chamber right here. That's this metal cylinder up here. We accelerated a beam of helium-3 into the target. And then we looked at the triton reaction products, which keep going forward and get momentum analyzed by the magnetic field of the spectrograph and get detected at a detector here at the focal plane. And from the radius of curvature of how those guys bend, that's directly related to their kinetic energy. And because of energy conservation, that's directly related to the excited state of neon-19 rather, that gets produced in the reaction that's still stuck here in the target. And then furthermore, we surround the target with those same kinds of solid state thin silicon detectors so that if we produce an excited state that then emits an alpha particle or a proton or something like that, we can detect that decay. And so in some sense, we're sort of doing the reverse of the actual reaction. We're producing neon-19 and then looking at the alpha decay that goes to the oxygen 15. And so this was the thesis project of my student Kang, and this is, I'm skipping a lot of steps, but this is the spectrum of this excited states that get produced. So this is like basically, the y-axis is how many counts you see as a function of position along that focal plane, which is the same thing again as saying as a function of the excitation energy in the neon-19 nucleus that gets produced. And this is important for a couple different reasons. One is the oxygen 15 alpha gamma reaction. And this is the specific state that totally dominates that reaction rate, which we were able to produce. And then there's a different reaction, which I should have mentioned on the last page, which is fluorine 18p alpha. And fluorine 18 plus a proton produces those same states in neon-19, but higher in energy. And this is actually super important because fluorine 18 is produced in classical novae, which is a very similar explosion as X-ray bursts, except instead of a neutron star, it's a white dwarf star, but otherwise very similar. And you can see gamma rays that get produced in these states with gamma ray satellites. And one of those is a 511 gamma ray that primarily comes from this fluorine 18 isotope, but it can be destroyed via this reaction. And this is the most uncertain aspect of how much of that gamma ray is produced that gets observed in the galaxy. And it's kind of an unknown thing. And so these states up here are responsible for that reaction, which we also were able to measure. Oops. And so these guys here, I know this is again a lot, but the blue is the same exact spectrum as this guy up here. It's just in a log scale, so it looks a little different. And then below it, the black lines are basically the number of times that state emits an alpha particle as it decays that we detect in that silicon array surrounding the target. And the red is the number of times it decays by emitting a proton. And so basically looking at the number of times you emit a proton gives us the information we need to calculate this reaction rate. And looking at the number of times it emits an alpha particle gives us the information we need to calculate this reaction rate. And so as you can see, if you recall, these two guys or this area region here was the most important for this fluorine 18p alpha reaction. And we see indeed those proton decays from this state. So we will be able to more accurately determine that reaction rate once his thesis is done, which I will hopefully be in the next month. And then we even maybe see a hint of this important state for oxygen 15 alpha gamma, but it might be background. So, we'll take it with a grain of salt for now. But it's an exciting result, and I'm excited to see what he finds out. So the other thing I was going to talk about, which I think I'm probably running out of time for, I'm guessing. Oh, all right, let's do this thing. Okay, so I didn't realize I had so much time. So that is sort of like a little snippet, if you will, of the work that's going on that we're doing on the RP process on the proton-rich side of the charter nucleus. But one of the other sort of really big areas of research right now in nuclear astrophysics, and indeed in the astrophysical community, has to do with how the heavier elements are produced on the neutron-rich side of nuclei. So if you think all the way back to the very beginning of my talk, when I was showing like the binding energy thing and blah, 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 we talked about how the only way that those heavy elements that were beyond the iron peak could be produced is if you added neutrons, because the Coulomb barrier was just not energetically favorable to add protons. And so that is exactly what the R process does. There's actually two processes. S process, can you guess? It's the slow neutron capture process. And that produces about half of them. And then there's the R process, which is the rapid neutron capture process. And of course, this is harder, so we'll talk about this one. And the reason it's harder is because, as you can see, you are so far from stable nuclei. And I don't think I ever knew this as an undergraduate, which I don't know if I should be embarrassed about or not, but a neutron that is not a nucleus is unstable. It only lasts for about 860 seconds before it decays. And so, at least over here, the protons and the alpha particles existed and we could make a target or whatever. But now you're talking about trying to measure reactions where both of the things that are reacting are unstable, and like, no way, like it's just not happening. Like, so these are extremely, you can't measure these things, okay, even though they're important. And there's a lot, again, of reactions that happen. So this is another one of these videos. You guys know how to interpret it now. The black boxes are stable guys. Things that light up are being created. And this is what happens in a theoretical R process where you're rapidly capturing neutrons. And when I say rapid, you can see that from the time scale here. Okay, we're at a few hundredths of a second, and already you're making all this stuff. And you're way far away from stability. And you can see, again, this buildup of isotopes at these magic numbers where things are real stable, relatively speaking. And then you go all the way up here. This is like where there's nothing, like no stable isotopes. So you're out past, uranium and all that good stuff. And still, now you've just reached a second, and now the process is stopped and everything's decaying back to stability. So rapid is for real, like it's rapid. And what you end up with is this sort of pattern of isotopic abundances that gets produced. So the red is what gets produced in this rapid neutron capture process. The blue is what gets produced in that slow neutron capture process that happens way closer to stability and much slower. And so the peaks are offset because of that. So where does this happen? So for a long, long time, even like before my time, people were real convinced that this sort of rapid neutron capture process happened in core collapse supernova. That was like what was taught to people in school. Like it was the, word on the street, like this is what happens. And people were pretty convinced that it happened in a single environment, because when you looked at observations of very metal poor halo stars, so what does that mean? Like those are stars, according to my friends that are actually astrophysicists, that exist in the halo of the galaxy that are very, very, very old. And what that means is that likely when they were formed, they were formed out of the initial stuff of the cosmos, aka hydrogen and helium and that little bit of beryllium and lithium that we talked about earlier, and maybe the ashes of a single star that had died and exploded and gone into the interstellar medium. So in some sense, looking at anything above the sort of lower light hydrogen helium isotopes was looking at the ashes of a single stellar event. And what they found when they looked at that and looked at these various isotopic abundances, this is, it looks kind of the same, but more instructive is this guy down here. You look at the residuals, they basically have identical isotopic abundances. So people were pretty convinced it happened in one place. The only candidate was, core collapse supernovae. For some of the lighter isotopes, the story was not so clear. And the thought is that there are other processes happening down here, which, are currently an active area of study. But then when people started to do more and more simulations and understand core collapse supernova better, it turned out that there just weren't enough neutrons when these explosions happened to make this kind of a process go and produce these isotopes. And so people started looking around at other options. And what went into those options and those models was, of course, again, the nuclear physics that drives these things. And of course, these reaction rates for neutron capture, where you just absorb a neutron and emit a photon, similar to the P gamma reactions we were talking about for X-ray bursts, play a role. But again, those are impossible to measure, so they're all theoretical. But there are other pieces of nuclear data information that can be measured and are currently actively being studied that are also required. And this includes the mass of these really radioactive species, many of which have not been measured before and are just being measured now for the first time, how fast they decay, and these so-called PN values, which basically says, okay, I'm a super neutron-rich nucleus and I'm going to decay. Am I just going to decay by emitting a beta particle and changing one of my neutrons into a proton? Or will I do that and then emit a neutron on top of it? And that changes basically where you end up on stability after you decay back to stability to get that isotopic pattern we were looking at earlier. And so you need to know which do you zig or do you zag to basically try to reproduce those observations in your models. And so for a long time, they thought it was against core collapse supernova. That turned out not to necessarily be the right answer. And so people were looking at other sites, one of which was neutron-star mergers, but none had been observed, for one thing. And there was not a clear evidence if there could be enough to produce the amount of our process abundances that we see in the world, or if you would actually be able to see some signature of the R process even happening until, thanks to LIGO, we observed the first neutron-star merger event back in 2017, I want to say, maybe 2019. Anyway, I'm contractually obligated to show LIGO slides since I'm from LSU. So for those of you who aren't familiar, LIGO is the Laser Interferometry Gravitational Wave Observatory, or something like that. And it's big Michelson interferometer, and by big, I mean the arm lengths are 4 kilometers long. One of the sites is in Livingston, and the other site is in Hanford, Washington, which is much less green, so I always show the Livingston image. And they were able to successfully detect massive black hole mergers after the advanced LIGO was up and running. That was probably the 2017 one. And then a few years later, they detected their first neutron-star merger, which was super duper exciting for all of us in nuclear astrophysics who had been postulating that this might be a site of the R process. But who can say? And so this is the observation. And the first time I showed this slide in a talk, which was right after it happened, I was sitting there yammering on about how great the signal is. And then I noticed that there's no signal in the third detector, which is the Virgo Observatory, similar setup as LIGO, but in Italy. And I was oh God, please don't let anybody ask about this. And nobody did, thank God. And then afterwards, I was I went to the former spokesperson of LIGO, who is one of my colleagues at LSU. And I was what is the deal, right? And she's actually, it was a non-observation. And the big thing about this neutron-star merger event that was observed in LIGO is that they were able to find in the sky the event after with telescopes and satellites and take optical and infra, all kinds of different spectra with more traditional telescopes. And they actually saw signatures of the R process in the light curve that came from that. And the reason they were able to do that is because they didn't see something in Virgo. And it all has to do with the orientation of the arms. And if you see a signal, and there is a much more limited region of the sky where you would get these two detections and not that. And that let them really pinpoint very, very quickly where the event had taken place in the night sky and point everybody towards there and get all this observational data. So it's kind of amazing. And now I know that, so I don't feel like an idiot when I show this slide, which is good. So they've also now since observed several other neutron-star mergers, and in one case, again, got another optical or another E&M follow-up. So it's a really exciting time to actually be able to get some observational data that actually links directly with the nuclear physics and the models that come from that and better understand the R process. Oops. And so this beta delayed neutron emission that I was talking about, this PN values, is something we're actively studying at LSU. I won't go into these slides in too much depth because, again, I'm running out of time. But the basic idea is that you can basically you can make some of these really neutron-rich isotopes in various accelerators or with a really neutron-rich radioactive source, but you don't make a lot. So you can't do like a reaction rate study like I would do for like the X-ray burst stuff. But you can study these like basic fundamental properties of the nuclei. And one way to do that is to trap them and then watch them decay. And so they came up with this method called recoil ion spectroscopy, where they trap an isotope and then they look at its decay. And you can basically figure out what percentage of the time it just decays via beta emission and what percentage of the time it decays via beta emission followed by a neutron emission. And the way they do it is pretty smart. I keep saying they because it's one of my, I'm very peripherally involved, and one of my colleagues at LSU is really doing this work more fundamentally. But let's say you just emit beta, right? You emit a beta, a neutrino, because you have to for reasons, and then you detect the isotope. So beta goes one way, neutrino goes one way, and then conservation of momentum. You get the leftover isotope, the daughter, going the way. You detect the beta and you detect the daughter, and that there you go. If you then, after you emit the beta, then emit a neutron, not only can that change the direction of travel, but because of conservation of momentum, your daughter nucleus, the xenon 136 in this case, that decayed from the iodine 137 emitting a beta and then a neutron, gets an extra kick. And that means it gets to this detector faster. So if you see a beta and you say, start my clock and wait for an ion, what you see is that this comes much, much faster, or should come much, much faster than the guy that just emitted a beta particle. And in fact, in the proof of principle experiment that we did almost a decade or more than a decade ago now, you see exactly that. So this peak is from just emitting a beta decay. And then this guy that happens way faster, a couple microseconds, but nuclear scales, that's a long time, is from beta delayed neutron emission. And so you can get that PN value that feeds directly into these models and gets you a better sense of how the R process is working. And so this was done with like a trap that was made for a totally different purpose. And then the geniuses at Argonne came up with this idea and tried it out. And now we are partners with them and a group from Livermore building a new dedicated trap that is expressly built for this purpose. And so it improves on efficiencies, it improves all these kinds of things, and we'll be able to go up like to way more nucleons and way more neutron-rich nuclei to understand better the R process. Okay, so that's everything I wanted to say, which is amazing that I got through it. So I hope I've convinced you that it's a really interesting multidisciplinary field. There's so much to do. We're just sort of scratching the surface. Just in the last couple of years, the next generation facility in the United States, the facility for rare isotope beams at Michigan State, started taking data. And that is designed to be a radioactive ion beam facility. So it's opening up like all new parts of the chart of nuclides that we can now study experimentally, which is a really exciting time. But there's still a lot to be done. And hopefully that will mean that we all stay employed for a long time and get grant money. But thank you guys for listening. This is a lot of the collaborators that were involved in the specific work that I showed. Probably miss people. And happy Mardi Gras for Louisiana. We have a great university. If any of y'all are interested in grad school, we have a great grad program. You can come talk to me about it. But if you have any questions about that or anything I talked about, I'm happy to answer them. That's a good question. So the current facility at Argonne where this data was taken, it came from a californium source, which fissions into two kind of neutron-rich parts and has a whole like variety of things that gets emitted during that fission process. And so basically what happens is that gets extracted from where the source is, and then exactly what you say, basically, we use magnets basically to direct the specific isotope, which has specific mass over charge ratio, which the magnet can select for, and then it gets accelerated just a little bit and then slowed down, and then the trap itself is a bunch of like RF kind of resonatory things that basically balance the electric and magnetic fields to keep it put until it decays.
Have you, this has been tested with multiple different stable elements, or have you, like, how do you pick which ones to use to the best result?
Like for indirect measurements and stuff, it's sort of like a, I would say it's a mix between like what's technically feasible, and can give you good statistics and that kind of stuff, and what is selective for what you want. So like there's I guess a longer answer is there's a lot of reactions that could produce a specific isotope that you're interested in, but certain reactions might produce the states of that isotope that really matter for the reaction you're studying. So a good example might be, like, let's say I care about a P gamma reaction, right? So like a nucleus that absorbs a proton and creates excited states in the spinal nucleus. But that is impossible to study because the beam doesn't exist, blah, 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 whatever. I could do, if the beam does exist, I could do a helium-3 beam looking at the deuterons that come out that has a much higher cross section, but is doing the same thing effectively in that it's adding a proton to the neutron. And that will, in theory, more selectively give me the nuclei of interest in the same, with the same properties or in the same states of what would happen in the star. So there are things like that to also consider, but a lot of it is, quite frankly, like technical considerations, like what's possible. And so a lot of times you'll have, especially for these kind of more important reactions that everybody's trying to get after that are more impactful, you'll have, 3, 4, 5 different types of reactions that people have tried to use to get at this information. And it's interesting because, different reactions might yield different results, and then there's disagreements and people are fighting at conferences and so there's a lot of, it will also somewhat depend on that. Like, let's say there's a discrepancy between 2 measurements. Maybe you are like, okay, I'm going to try from approach 3 and see who I agree with and that kind of thing.
Instead of when you're dealing with these collision experiments, instead of measuring like spectroscopy, like measuring discrete energies of photons, you're measuring the discrete energies of alpha particles and protons that come off of these reactions. Is that correct?
Almost, yeah. I mean, so the discrete energies are really the energy of the excited nucleus. That's the heavier guy that gets produced, and then so the kinetic energies of those protons and neutrons are the discrete things that you're measuring. Like those guys are typically just in their ground state, but their kinetic energies will be those sort of discrete energies related to the states of interest. Yeah. So that's exactly right. Yeah. Yeah, I think so.
How many are you postgraduate opportunities that you have?
I would, yes. So we have an RU program, which you can hear all about because our friend there has already been through it a couple of years ago. And it's, I mean, I'm obviously totally biased, but I think it's a great program. We typically in the actual RU program have about 10, I think 10 or 12 students. Is that how many you remember from your? Yeah. But then we also have, like, we open it up, like the activities to our local students who have chosen to stay at LSU to do research over the summer. So it ends up being kind of a bigger group functionally speaking. We have lecture series every Thursday afternoon. You'll get a lecture from one of the faculty members, whether you like it or not. And then we have like a lot of other like professional development stuff that we do. We have fun stuff that we do. Like typically one weekend, we take the students on a swamp tour because it's Louisiana and you have to do these things. I think one weekend they went to New Orleans, fun stuff that, is important for a well-balanced life. It's hot, but we have air conditioning. Yeah, but it's fun. And then, yeah, we have a very large graduate program as well. Like, I mean, there's obviously nuclear physics, but we have a really wide variety of really top-notch research programs from materials and condensed matter. It's a physics and astronomy department. So we have a lot of astronomy and astrophysics, from modeling to observations to other, more like instrumentation stuff for satellites that are growing up and that kind of thing. LIGO, of course, and particle physics, neutrino guys. I mean, medical physics, we have a big medical physics program. So we have incoming classes every year, about 15 to 17 graduate students or so. And it's, again, I think it's a great program because I'm 100% biased, but you should apply.